So of course, I'd like to thank Mohit and all the other organizers for this honor to speak at this meeting, felicitating TVR. And this is some story we have been going back to from time to time over the last 10 years or so. Started with the work of Sambuddha Sanyal. And more recently, there's a whole bunch of students who worked on it, primarily Shaunak Biswas, Ritesh Bhola, Mursalin Islam, and also some work by Zahid Ansari and Shauvik Kundu. And it's about a kind of percolation problem, which we think has interesting implications for transport and magnetism. And that's what I hope to convince you about. So I don't need to remind anybody in this audience that disorder is kind of a ubiquitous part of condensed matter systems, although we try to minimize its effects. Strong disorder, on the other hand, we know can lead to new phases of matter as well, things like spin glasses. And even when it doesn't do that, it can probe correlations of the underlying state. If the underlying state is some sort of spin liquid, which has no definite positive signature, let's say neutron scattering, then having some spin textures developed because of some impurities can give you a diagnostic about what kind of liquid it is. Right? So it can be a nuisance, it can lead to new phases, it can also be a probe. The part of this disorder effect story that we tend to take for granted is what I'm calling in quotes the central dogma, which is the idea that if you sort of have an identical protocol that you don't change and you make many samples with the same protocol, so that the same kind of disorder gets introduced into each sample, then we expect that physical properties are self-averaging in the large size limit. If you make a big sample and you make 100 of them in an identical way, okay, it has some dirt in it, but the concentration of the dirt is not going to change from sample to sample, and physical properties are going to have small sample to sample fluctuations relative to their average or typical value across the sample. This is something we kind of take for granted. Of course, it's not a theorem, it's a dogma because violations do exist. We know examples where the sample to sample fluctuations, if you plot them as a distribution, it's a very broad distribution. We also have a weaker version then of this dogma, which is that at a minimum, at least all samples made identically will be in the same phase of matter, even if the distribution is broad. But maybe there are exceptions even to that. I'm not an expert. This is something people argue about, I think, in the spin glass literature. But then it gets entangled with questions about what do you mean by the same phase of matter in the context of a spin glass. So I don't want to get into all that. That's why I'm calling it a dogma. And it's this weak version that I want you to keep in mind, that at a minimum, all the samples you make should be in the same phase of matter. And what the reason I bring this up is I'm going to claim later in this talk that we have come across an example where this doesn't seem to happen. And we don't fully understand it, and we think it has implications for transport. So that's the goal of the talk, to convince you of that. And this has to do with a kind of, like I said, a percolation problem. So let me first just say a few things about percolation. Percolation is simply the question about whether you can go from one end of the sample to another if the sample has sort of blocked pathways and regions you can't access and things like that. Right? So it's the simplest, if you wish, and completely geometric example of a phase transition, because you can go from a regime, as a function of the disorder, you can go from a regime where you can walk from one end to the other to a regime where you cannot, right? And the mathematical model for this, introduced many decades ago by mathematicians, was that you just take a regular lattice, let's say the square grid, and you randomly remove sites or bonds with some probability. This is the density of vacancies for me, NV. This goes by the name of Bernoulli percolation. Bernoulli simply means what you take out is uncorrelated. It's random disorder completely. And the answer to this question, yes or no, right, is the actual order parameter for the transition, if you wish. This Boolean variable, which is the yes-no answer to this connectivity question, that's what you monitor. And the probability that the answer is yes, that means the probability you can go from one end to the other, I'm calling P of L. L is the linear size of your sample, and NV, which is the density of vacancies. And this is the quantity that's sensitive to this transition. And so the nice thing about this very simple geometric example is that this probability, at least in these simple models, collapses onto this sort of scaling function in the vicinity of a sharply defined transition point. And basically, for low enough dilution, the probability that you can go from one end to the other is 1 in the thermodynamic limit. And for high enough disorder, it's 0. And then in the middle, there's a critical point, and there's the scaling. And there's other features that are specific to sort of these simple models, which is that the probability P can only be 0 or 1 in the thermodynamic limit. It can't take any other value. And the fact that there's exactly one percolated phase and one unpercolated phase as a function of the density of vacancies, and that means no re-entrant transitions. So these are properties of a simple model, if you wish, of percolation. They don't have to always hold, but they hold in almost everything everybody has looked at. And our basic message is that if you look at a particular percolation problem, which is the percolation problem in the random geometry of what I call maximum density dimer packings of weakly diluted lattices, and I'll say what that is with pictures in a minute. There is an unusual percolation transition, and in the percolated phase, you have violations of even the weak form of what I was calling the central dogma. That means some of the samples are in a different phase of matter from the other samples. And the root cause of this, I hope to convince you, is that there are severe kinematic constraints that somehow induce long-range correlations, which we are not fully able to understand, but that must be the cause. And the further claim is then that this phenomenon should have some consequences both in transport and magnetism. Specifically, if you imagine P plus IP superconductor in its topological phase, so that every vortex has a Majorana mode at its core, and you're in the mixed phase of this P plus IP superconductor, so there's a triangular vortex lattice, and it's sort of disordered because of some pinning potentials. Then if you have vacancy disorder in this vortex lattice, some missing vortices, some slight inhomogeneities in the density of vortices, some missing vortices, then in the thermal conductivity of such samples, there will be a contribution that will exist in half the samples and not exist in the other half. So the thermal conductivity is going to be, bimodal if you plot its distribution as a function of samples. So half the samples will do this, the other half won't. And that's because the Majorana part of the system can be in two phases. It can be delocalized or it can be localized. That's the claim here. And also the Majorana part of this story is going to have a sort of a chaotic response to any change in the disorder. Yeah. Well, I just mean something where the bond lengths are not regular, so the disorder is slightly, there's positional disorder, which has pinned. So they're not moving, they're pinned. Yes, there are memories, but the bond lengths have jitter. That's all I'm relying on. So it's a triangular lattice with jitter in the bond lengths and angles, but still recognizably a triangular lattice. And then there are some missing vortices. That's the. And then there's a kind of a side story about similar effects arising in RVB spin liquids, but maybe I shouldn't talk about that here and focus on the localization part. So we started thinking about this in some very roundabout way because of a side story in the localization literature that has to do with particle hole symmetric localization. There's a very, very long history. And sort of the main paper on this was this work by Gade using methods of Wegener, and there's a follow-up with Gade and Wegener, which I didn't mention here. And the claim here was that at the band center, so if you have bipartite or particle hole symmetry, then the band center zero energy is special because the spectrum is symmetric. Epsilon equal to 0 states always have a partner at epsilon equal to minus. So plus epsilon and minus epsilon are partner states, and epsilon equal to 0 is special. And so something funny does happen to the density of states in these bipartite hopping problems, random hopping problems, near zero energy. And there were detailed field theoretical calculations that gave a particular density of states, divergence, and then, there's a long story correcting some fine details of it. But the point is, there was a more recent claim from the group of Merlin and Ferdy Evers, saying that if you have dilution, not just random hopping, uh, it completely changes the asymptotics of this side story. And so we were interested in this because symmetries are unchanged, and the general dogma is that, if the symmetry class of this localization problem doesn't change, then the asymptotic answer shouldn't change. So we were wondering how these claims arise, whether they are true. And when we looked at it, we realized, so this is what I'm concretely talking about. You, for example, imagine the tight binding model for undoped graphene with just nearest neighbor hopping kept, not next nearest neighbor hopping, just as a toy model. And there's some disorder in the hopping amplitudes. So this has particle hole symmetry, and you ask what's the density of states near zero energy, with and without random vacancies. So vacancies simply means some of the orbitals are just missing, sites are removed from the honeycomb lattice. And what we realized is that if you have some small amount of vacancy disorder, this is 2%, 4%, 6%, like that, there's a density of zero modes. And these are pinned to the band center. So the density of states, if you wish, is made up of two parts. There's a regular part, and there's simply a delta function, like that. And this is really a density per unit area. So this is thermodynamically significant, and it has some dependence on the density. And somehow these funny effects that were being talked about in these papers had to do with a crossover coming from the presence of these zero modes. That's a different story, but that's how we started thinking about these zero modes. And we were wondering where they come from. And, because initially we were very surprised that there are modes that are strictly pinned to the band center in the middle of a continuum, because, that's not supposed to happen. But we heard talks yesterday, of course, where that does happen in other contexts, like this Lieb lattice and this STM data on it. So something similar was going on here, and we were trying to wonder where this comes from. And we made some, we drew some pictures, tried to make some guesses. And so here I'm showing two guesses. So these circles are supposed to be where the vacancies are, and I'm drawing the honeycomb lattice sort of in brick wall notation. Yeah, it is the honeycomb lattice as far as connectivity goes, but I've just drawn it like a brick wall. So if you have 4 vacancies that cluster in a particular way, you can just construct by hand a zero mode wave function that lives entirely in this region. You have 6 vacancies that cluster in some way, you again can write some wave functions down, and this was not going anywhere because you can keep drawing pictures. These are all extremely unlikely configurations, but you can get zero modes. But by drawing such pictures, we realized that there's a key distinction between, for example, the picture on the left and the picture on the right. This picture, this zero mode just disappears. It leaks out into the bulk and doesn't remain at zero energy if there's any jitter in the hopping amplitude. So with bond disorder, this is just no good. But this one, no matter what you do to the bond disorder, you can make the TIJs whatever you like. There's always a zero mode that lives only in this triangle, only its wave function changes a little bit. So it's stable in that sense. As long as a non-zero hopping amplitude remains non-zero, its value can do what it likes. Zero hopping amplitudes remain zero. This mode survives. So we kind of conjectured that this very stable density of states we were seeing came from modes like this, but not, of course, this picture, because we are just randomly diluting the lattice. We don't know what dominates, but things like this dominate was the conjecture. And we tried to make that a bit more precise by saying, look, there is a general reason this can happen, which goes back to sort of the first course on linear algebra in your BSc course. If you have a bipartite lattice and you randomly dilute it, globally you can demand that the number of A sites equals the number of B sites, but you can't demand that locally. So there's always going to be regions of local sublattice imbalance, and that's going to happen quite often. But there can be rare regions of local sublattice imbalance. And the rarity of these comes from the fact that although the number of A sites dominates over the number of B sites in this region as a whole, the boundary of the sample is only made up of B sites. So the boundary is the minority sites locally, and the other sublattice wins. So this is rare. And so we asked what this would do, and it's very easy to see that every time you have such a region, this local imbalance, that's the number of zero modes you can make that live entirely in this region. And this just comes from sort of asking how many variables you have at your disposal to write down zero mode wave functions, that's NA, and how many constraints does the Schrodinger equation at zero energy impose, that's NB, and that's it. So you always get these modes, and because it's just constraint counting that's determining the modes exist, they're completely stable to bond disorder. But this doesn't take us very far because these are just hand-drawn examples I drew, and then I conjectured a general sort of mechanism. But are these really there in a randomly diluted sample? What density do they occur with? What shapes do they have? None of this was clear. But the fact that it's coming from local sublattice imbalance gave us a bit of a clue. And the fact that they only depend on connectivity, not hopping strength. So we asked ourselves, how do you diagnose where local sublattice imbalance exists? And we were helped by the literature. Other people had been thinking about the same thing for many decades, it turned out. And to cut a long story short, the idea is you have to think in terms of matchings or dimer covers. Because a dimer is a hard rod that lives on a link of a lattice that connects a side to one of his B neighbors. So it's something that enforces sublattice balance locally, right? So if you could pack a region of the graph with dimers, fully pack it so that no vertex is left free, then you would never have any sublattice imbalance even at the smallest scales in that region. So you should look for regions of the graph that cannot have perfect matchings or fully packed dimer covers. And those are the regions which could be these. Yeah. Yes. So the idea here was that what is the topology of a graph? Well, it's where there is a connection when where there is no connection. So if you think of the hopping matrix, you fix the position of the zeros in that matrix, but the non-zeros are determined, non-zeros can do what they like, as long as they are non-zero and the zeros are zero. Yeah, so the meaning here is more sort of graph theoretic. It's the idea that the connectivity pattern is the topology and the values of the connections are the geometry. Well, that's of course different from other notions of topology, but here all I mean to say is that it is insensitive to the values of the non-zero hopping elements, cares only about which ones are zero and which ones are non-zero, right? In that sense, yes. And so this was a good way to think. And so let me just say for people who don't think about these things often, fully packed dimers simply means you try to put hard rods down on links of the lattice so that every site is covered. In computer science, that's called the problem of perfect matchings. And typically on a regular graph, there's an entire entropy density of such matchings or fully packed dimer covers. It goes back in statistical mechanics to classic papers of Castellan and Fisher and more recent work. But if you have a disordered lattice, can you even do this, right? It's not clear. So in general, it turns out that you can't fully pack a lattice with dimers if you have disorder. The best you can do is make a maximum matching, not a perfect matching. So some minimum number of vertices have to be left free, don't have dimers on them. And so in this language of dimers, you would say they host the monomers of that maximum, that maximally packed dimer cover. It has some monomers somewhere, and these unmatched sites are where they live, right? And of course, they can move around. There's a whole entropy density of maximum matchings as well. And so the idea was then that you try to study this problem instead of the original problem and ask where the monomers live. Ask where the monomers of maximum matchings live. And that tells you something about where the zero modes are. That was the idea. And the key observation that sort of gives credence to this way of thinking is that these regions I was drawing earlier, which I gave a simple linear algebra argument for why they must host so many zero modes inside it, fully localized inside it. You can see just from their local structure, must also have the same number of monomers inside it. There's no way you can match more than NB vertices, NB of the NA vertices with dimers here. So you must have these many monomers inside these regions as well. So you're sort of saying that locally they're the same thing. And it turns out there's a long history of thinking like this that goes back to Longuet-Higgins, but not at the local level. So while thinking about the molecular orbital theory of some benzene-like molecules, he was asking which one of them are magnetic and which one of them are not magnetic. And he basically made, in our language, the following statement. He said the total number of monomers in any maximum matching equals the total number of topologically protected zero modes. This is not the language he used, but I'm just translating what he says to our language. This is a global statement. This was all he needed because he just needed to identify whether or not there are monomers in the maximum matching problem of a particular molecule in molecular orbital theory. And then if there were monomers, he would say, yes, this is a magnetic molecule, that one is not. That was the idea of this paper. So he just needed this global statement. We are interested in a bit more. We want local information, right? We want to know the wave functions. So the question we are asking is, where do these zero modes live? Where do the monomers live? And what I mean by R type is these regions I was drawing. R is supposed to stand for robust zero modes, just for historical reasons. But this is not a well-defined question. What do you mean when you say where does the wave function live when there's a large degeneracy of wave functions at that energy? Any linear combination is also a wave function at that energy. So what we are really trying to say is we are trying to ask if there's a nice or useful maximally localized basis for these wave functions. Can we construct a basis for these wave functions which has support? Individual elements of that basis only have support inside a single region of this kind. That's what we are asking. And there's a related question that we came to more recently, which is more relevant for this P plus IP superconductor. So let me mention that as well. So if you have some of these systems where you have, for topological reasons, and now I'm using topology in a different sense, you have these localized Majorana modes that are seeded by defects in the bulk. And then, of course, if two vortices are far away, let's say in a P plus IP, they don't mix and you have these Majorana modes. But if they are nearby, like in a vortex lattice, there will be some mixing between them. And in general, the mixing problem can be thought of as a sort of a tight binding model for these Majorana mode. And so these are Majorana operators, Majorana fermion operators. This is their mixing. And by more or less construction, because these are Majorana fermions, this matrix must be pure imaginary and antisymmetric. So I times A is a pure imaginary antisymmetric matrix that defines, if you wish, the tight binding model for these Majorana. And this is a generic sort of way of writing down several things which people have been thinking about. So for example, mixing of Majorana modes in this vortex lattice, or Majorana excitations in Majorana spin liquid states. The zeroth order description of all this is some tight binding model like this, right? So now usually a matrix like this generically will have non-zero matrix elements, non-zero eigenvalues, which will come in pairs epsilon and minus epsilon. And then you would say that the Majorana modes are destroyed by the mixing. But every once in a while, you could have zero modes of this matrix that are, again, protected, topologically protected. And they would have the interpretation of collective Majorana modes. Yes? Sure. Well, that's a question of what we mean by zero in zero, what is zero energy, right? So in particular, you might be doing some experiment at some temperature. So everything much less than T is zero and everything of order T and non-zero, something like that. So given the context, you have some effective description like this. That's all I'm saying. The regular bit by definition is the regular bit, and whatever I get other than that, I'm plugging into this. So what you're really saying is, depending on what assumptions I make about what mixes with what, the value of W can change and the form of this can change. Yes. Sure. Yeah, of course. But I don't think there's any sense in which, if you look at these mixing amplitudes, the ones mixing two vortices very far away are as important than the ones mixing the ones that, right? Absolutely. So that just, that's a mathematical idealization that says, give me the mixing matrix and I'll tell you what I mean, right? Of course, given the context, what you write down as the mixing matrix will change, of course, right? Even in the honeycomb problem, there's next nearest neighbor hopping, there's other things. It's always there. Now, the basic picture for these collective Majorana modes is a little bit different. So let me just flash that. Every triangle in the sort of connectivity of this graph or this matrix will host a Majorana mode for, again, trivial linear algebra regions. You have an anti-symmetric matrix, 3 by 3, there's got to be something at 0, right? But then they mix. And if you can find regions where the number of so-called triangles, it's not really triangles, I'm just calling them that. Those of you who know some computer science, I'm actually talking about blossoms. So if the number of blossoms outweighs the number of other kinds of sites, then locally you will have a collective Majorana mode. That's the basic picture. And again, there's a way of thinking about it graphically, as well as in terms of maximum matchings, because you make the observation that if you have regions like this, it also traps two monomers. This one has two zero modes. It also has two monomers. So again, there's a local correspondence. And again, this gels with what's been known for a long time in the computer science literature, which is the global statement. The global statement is total monomer number of maximum matchings equals the total number of topologically protected zero modes. Again, this is not the language in which this is written, but that's what it's saying. So again, we want more information, we want local information, and that comes from thinking like this. So this was background. How much time do I have? 8 minutes. Yeah. So this sets up what I want to do. So now I'm interested in studying this problem of monomers, of maximum density dimer packings, of the whole ensemble, with weak vacancy disorder or bond dilution. And I'm going to ask, where do the monomers live? That's the goal here. And so now let's just take an example of what I was talking about. So what I've done is drawn a sort of an extremely diluted triangular lattice, so that all the sites have got basically knocked off and this small fragment survives. So all the dotted lines don't exist, all the intersections of dotted lines are missing sites, and then these bold dots are the sites that survive, and these are the links between them, right? So now you start putting dimers down and you want to put as many down as possible. You realize very quickly that you can't do better than leave 3 vertices unmatched. So there's got to be 3 monomers in this no matter what you try, and you can try this and play around and you can't do better, right? So the maximum matching here is a deficiency of 3. You need 3 monomers. Where do the monomers live is kind of up to you at some level, because given a monomer somewhere, you can always follow an alternating path like this to hop the monomer along it. So no dimer, dimer, no dimer, dimer. You can hop it by sliding all the dimers forward, and the monomer would go there, right? You can always do that. Similarly, if you have a loop of dimers like this, which is an alternating loop, you can flip it and you can get a new configuration. So you can now start playing around and ask, where can I take this monomer? Where can I take that one? Where can I take this? And this is not going to be a proof, but if you think about it for a minute, you'll say you can't do everything you like. You can do a few things, like I can take this pair of parallel dimers and rotate them so that they become vertical. You can take this monomer here, let's say, or here. You can take this monomer there, and so on. So you can do things, and that's why there's an entropy density worth of maximum matchings, mostly, in most graphs. But you can't do everything. And so the sort of more formal way of saying this is that there's very constrained kinematics. All you can do is these ring exchange moves of dimers or monomer hopping along alternating paths. And the constraint on the links that participate either in a ring exchange or in a monomer hopping path is a sort of an obvious one, but worth stating. Each such link must be occupiable by a dimer in some maximum matching, right? Because that's what you're doing. You're moving things along. So there'll be a different maximum matching where this link is occupied by dimer. So unless there is that possibility, such a link cannot participate in a move, right? So this is an obvious thing, but worth stating. And this is what really leads to constraints on the dimer motion. You will find that these monomers are really constrained to live only in well-defined regions of the lattice. So what defines those regions is that there are forbidden links of the disordered lattice which can never have a dimer on them if you want to reach maximum density. somehow the idea of having full packing is out of the window, but you want a maximum packing, and you can't reach the maximum if you put a dimer on one of these links. So for example, in this picture, you can do whatever you like, but if you put a dimer on this link, you will never be able to fill enough dimers in to reach the maximum density. This one. Between green and blue, the link that connects green and blue, you will never be able to put a dimer there. Similarly, the link that connects pink and blue, you will never be able to put a dimer there. So there are these forbidden links. And in fact, they define for you the boundaries of these regions I'm talking about. So if you just cut them, your connected graph will break up into regions. And these regions will be these R-type regions that host some fixed number of monomers inside them, and other P-type regions that are always perfectly matched. Okay, and this can all be made very formal, and this is not the point of the talk, so I'm just flashing this slide to show you some references and names. But let me go ahead and just say we have a way, a well-defined way of identifying these regions, right, algorithmically. And so again, to repeat, what is the significance of defining these regions? Well, these R-type regions host the topologically protected zero-energy states in any bipartite random hopping problem. And such modes are guaranteed not to live in these P-type regions, which are the complements. And so this has implications for transported zero energy then. And this is what I was saying earlier, that in the Majorana problem as well, each R-type region is guaranteed to have a certain number of collective Majorana modes. The P-type regions are guaranteed not to. And these are now tractable computations. I'm not doing any matrix diagonalizations. I'm just doing this combinatorics, identifying these regions. So we've done that. And we then look at it from the point of percolation, because we find the typical size of these R and P regions is very, very, very large as the dilution is small, as the disorder is weak. So those pictures I was drawing by hand are completely misleading. So let me focus on the case where we think there is some interesting physics, which is a weakly diluted triangular lattice. So if I look at this connectivity question, can I go from one end to the other through a single region? I don't care whether it's R or P to begin with. Can I go from one end to the region, one end to the other? It turns out there's a very sharp transition. Above this dilution, the probability of going from one end to the other drops to 0 in the thermodynamic limit. And below, it goes to 1. And so there's a weakly diluted regime where you can always go from one end to the other in the thermodynamic regime. But I'm not telling you whether I go through an R-type sample or a P-type sample. I don't care at this point when I'm drawing this figure for this data. But when I look in more detail and I ask what lets me go from one end to the other, I find that in what I'm going to later call R-type samples, it's the largest region is an R-type region with monomers in it that spans the system, and I can go from one end to the other in that. And in the other kinds of samples, which I'm going to call P-type, the largest region is a P-type region with no monomers, no wave functions, that allows me to go from one end to the other. So there is this sort of, so I just randomly dilute the lattice and I make, I don't know, 10 to the 4 samples. Some fraction of them look one kind, the other look the other kind. And this is just ways of making that more precise. And here's a picture. So the color coding is consistent across the two pictures. This is an example of an R-type sample. This is an example of a P-type sample. Brown is the largest R-type region. This purple is the second largest R-type region. Blue is the largest P-type region. Green is the second largest P-type region. Yeah. Which is guaranteed not to have monomers in any maximum matching. The complement of R-type. So I break up the whole graph into a set of non-overlapping regions. R are the ones that have some fixed numbers of monomers in them. I can tell you how many in each. And P are the ones that are always perfectly matched. Yeah, so there's a entropy density inside it of packings. Yeah. So you can see they look very different. Yeah. Yeah, so I'll just come to that in a second here. So in fact, that was in this slide I flipped over. So this is the fraction that are R-type. And as a function of density of vacancies, dilution, you can see it's a little noisy. I don't have perfect data, but it's a flat curve at half. Half the samples have a percolating region through which the monomers can go from one end to the other. And the physical consequence of this is there's wave functions I can construct in this maximally localized basis that live entirely within this huge region. So I can't say anything sharp about their localization properties. But in the other half of samples, which are p-type, the biggest r-type region is like this. Like these. These are the biggest r-type regions, right? So they're tiny, and I can construct a basis of these wave functions that live entirely within one of them, right? So that means if I was calculating some basis-independent quantity like the Green's function that goes from one end to the other, right, that I need to do the Landauer calculation, that's going to be zero. That's going to be zero unless there's a brown region or a purple region that spans the lattice. So in samples like this, it doesn't. In samples like this, it does, right? So that's where this dichotomy comes from, which I believe has physical consequences. So we don't know why it's half. It could have been anything. In fact, it shouldn't be anything. It should be, all samples should behave statistically identically, would be our kind of belief, and that's getting violated. Yeah. Yes. So what I do is, so first of all, I've diluted the lattice. So there's already geometric clusters. But I'm deep in the percolated phase of the geometry. So I'm looking at the largest geometric cluster that spans the whole lattice and has a few holes in it. I mean, this is well below the percolation threshold of the lattice. Now, in that thing, I break that up into non-overlapping set of regions, R and P, right? And now I just do the percolation problem for these regions. Yes, yes, because geometrically it's all connected with some tiny holes in it. But because of these forbidden links, dynamically it's not connected. Yes. So yeah, you mean, sorry, yeah, I should clarify. So white doesn't mean that the lattice is broken up and there's holes there. It just means these are smaller R and P type regions that I've not bothered to color. The holes of the lattice are not visible on this scale. This is like some 10,000 by 10,000 system. So you won't see the holes of the lattice. They're very small. These white regions are, if I start coloring the third, the fourth, the fifth, the sixth largest one, then I would put colors inside there, right? That's what's happening. Yeah. Yeah, so that's exactly what, I don't know the answer to that. It's tempting to say there's an emergent symmetry there between monomer carrying and non-monomer carrying. I don't know. I mean, there are simpler problems where this happens for obvious reasons due to symmetry. I mean, we all know in classical statistical mechanics that you can write the Ising model as a percolation problem. It's called Fortuyn-Castellin representation of the Ising model, right? So the transition to ferromagnetism is the percolation transition of these so-called Fortuyn-Castellin clusters. And that sounds fancy, but all you're really doing is some Wolf cluster algorithm of Swenson-Wang cluster algorithm to simulate the Ising model, the type you teach, let's say if you're teaching Kraut's book. And then, the way these cluster algorithms work is you make the clusters first, you don't do anything about the spins. And then each cluster can independently be assigned all up spins or all down spins, right? So that's the Fortuyn-Castellin representation. So now from that point of view, this is a trivial statement in that problem, because you look at the percolation problem of these clusters, there's one percolating cluster, no problem. But then you're allowed to half the times say it's up spins and half the time say down spins. And that's just a representation of the Z2 symmetry. Here, there's nothing like that, but it's behaving like that, right? So I don't know why. I have no idea. But it has a consequence, and the claim is the heat conductance coming from these Majorana modes will be absent if the sample is p-type, present if it's r-type. So at the very least, you're going to get some very dramatic violations of self-averaging. So if I make a histogram of heat conductance in such thing, because there is a contribution that's missing in half the samples, I should just get two well-defined peaks, not even a single broad distribution, just two peaks. So it's in this sense that I'm saying half the samples are in one phase and the other half are in another phase. Right? That's the claim. And I said something about extreme sensitivity, so we've quantified that. We set the vacancies into motion. We just let them diffuse to a neighboring site. every once in a while, putting in some very strong constraints so that they don't change the overall geometry of the lattice much. So we are trying to play devil's advocate and do the minimum change to the vacancy configuration. So this is just to establish that I don't change the vacancy configuration doesn't change the geometry much. So this is looking at the size of the largest geometric cluster of the lattice. And you can see when I make the vacancies move, the way I'm making them move, this changes in like the 5th decimal place. 1 part in 10 to the 5, right? So it's not doing much to the underlying geometry. At the same time, what it does do is it makes R-type samples flip into P-type samples, P-type samples flip into R-type samples. As the course of this dynamics proceeds, R becomes P, P becomes R. They keep flipping. Now R and P are not regions, they are types of samples. So the largest cluster sometimes is R, sometimes is P, and it keeps flipping character and shape as well as I move these vacancies around. And this is the probability distribution of time steps after which it flips. So there's a rate, right? Now, what could this be due to? The only sort of dichotomous, yeah, just one last thing. You can think of this as answering questions. No, because I really am. You can think of this as what is the dichotomous variable that could affect this 50-50 thing, right? Only thing we could think of, because we know that in geometric percolation, almost everything is self-averaging in the percolated phase. The one thing that cannot be self-averaging is the parity of the number of sites in the largest geometric component. That, of course, is going to be half the times odd, half the times even. That's the only other 50-50 variable, which is a macroscopic variable, which which could have some chance of controlling this. So that's the variable gamma. So of course, as I make these vacancies move around, I said the size of the largest geometric component doesn't change, but its parity can change, and it flips, sure enough. So this is the probability of time steps, it flips on an average after 4 time steps, right? So both these things keep flipping, and then the question is, do they flip in a correlated way or not? And this is, you just make the product of these two icing variables and ask whether it flips or it's flat. If it was just flat, you would say the change in the parity of the geometric component controls what's happening. But it's not flat, it's also decaying to 0. A little bit slower, but it's decaying to 0. And you can also measure the cross correlator, and it just decays to 0. Cross correlator of these two Boolean variables. So this is saying that we don't have any macroscopic variable that we know or can identify that controls this macroscopic property of the sample, whether it allows conduction or not, right? But this is a deterministic thing. You give me the sample in its full detail, I can run Edmond's algorithm in time proportional to the cube of the number of sites in it and tell you what it will do. So this is entirely deterministic but completely unpredictable. And so this is why we are calling it chaotic. And there's other consequences, which I won't get into. Let me just stop here. Thank you. Yeah. Yes. Actually, it's very odd, right? Because the way I set it up, you will have realized, and that's why you're asking, that the wave functions have a product form where each component of the product lives in one region. Right? That's why you're asking this question. Okay. So if you take the Roxar-Kivelson Hamiltonian or any, not even Roxar-Kivelson, take any quantum diamond model defined on these maximum matchings with the proviso that you're allowed kinetic energy terms that flip any flippable loop. You choose which kind you want to flip, and you're allowed any interaction energies that live on flippable loops, right? And monomer interactions that live on flippable loops or alternating paths. You do this up to some range, there's some range restriction. Then the statement is that every eigenstate has a factorization where each piece of the ket lives in one region and one region only. So it's got a tensor product structure, which means if all R-type and P-type regions are small, nothing has percolated, you have area law entanglement entropy in the middle of the spectrum. But if something percolates, you'll have volume. So the percolation transition, which I didn't focus on much, is actually it's not MBL, I emphasize, but it is a transition in which in the middle of the spectrum, you go from volume law to area law. That's true. Yeah.
Yeah, you had some slides in which there was a statement about the topologically protected
Yes.
zero modes as the difference of two integers.
Yeah, you're thinking some
Atiyah
index theorem.
Index theorem, yeah.
So unfortunately, I couldn't cast it in that language. I don't know how to do that. Shubro maybe has something to say on the subject. No, Shubro was not listening. Yeah, no, I was joking. No, he's asking, is there an index theorem way of thinking about this?
So, no.
The boss says no.
Oh, it's not like that.
Huh?
No, the connection.
No, seriously, I don't know how to think about it like that because you see, this is very peculiar and at lattice scale, and I don't know how to even formulate the question like that. But it would be very interesting to ask what this is really is a rank nullity statement. Much more trivial. First year linear algebra course. That's all it is, nothing more. Right?
I have two questions, Kedar. So first is, I'm a little confused about this dilution part of it. So you mentioned that it's about, let's say I don't have an atom on the side.
In the toy model, yeah.
Yeah, in the toy model.
Yeah.
Or it could be that I've got bonds which are of different lengths.
Or you could have substituted one atom for another that doesn't have an orbital at the relevant energy, so doesn't participate in the tight binding.
So the diagram that you showed where you had the two R1, R2 and P regions, there it was only like removal of an atom, I suppose.
So
the lattice looked very uniform, at least.
You mean the pictures I was drawing?
Yeah, the pictures where you had two.
Yeah. So those like things I was drawing in the local train 10 years ago, and they mean nothing because they don't represent anything real. Actually, nothing really looks like that.
I think you just
this
meant,
one.
No, I meant where you had the two R region and P region.
This
forward, I think forward. You had these two colorings as well, right? Where you had the monomers left behind. Yeah, this picture.
Yes.
So here the lattice.
Oh, so here I've just taken an extreme example where I've knocked off everything and only one tiny fragment of the triangular lattice has survived.
Okay.
That's what I'm doing.
But any other case would also lead to the same thing as what you're saying.
Yeah, so what I'm trying to say is if you randomly dilute a triangular lattice at 2% level, then the things don't look small. They look like this. The regions look like this.
Yeah, the larger picture that you showed.
They look like this.
Yeah, got it.
Right?
One other question is, like you mentioned that if you had multiple systems with same kind of dilution, then you would, let's say I measure and you get two peaks like this.
Yeah.
Could I also think of this like a measurement problem in the sense that I measure some quantity, same system, but multiple times, and I'll still have like two peaks in my histogram?
Well, that depends on the time scale of your measurement, right? If your vacancy is annealed, if your disorder gets annealed a little, then effectively that's a new sample.
If I don't have annealing,
so then you're going to get the same answer. Then you're going to get the same answer. Every sample gives an answer. And what I mean by a sample is a certain configuration of defects. If that's going to move around a little, you have a new sample.
Okay.
Right?
Okay.
So it may not teach you anything, but you should probably take a bunch of your R and P type samples and do machine learning and try and see if you can.
We are doing that. Thank you. So the goal, it's a thank you. So I'm getting advice from Srijit and Piyush and so forth and doing exactly this. No, because it's ideally placed to do this, right? Yeah. That's a loaded question. You have something in mind. Yes. Yes, but they are perfect matchings, right? There's no notion of a monomer. Yeah. Okay. Yeah.
Okay. I think we can continue discussion with Kedar, obviously. There's lots of questions.
Thank you, TVR.
So